Hi there, my name is Miss Townsend and I love math. Welcome to Math with Townsend. This video is for grade 12 data management students who are reviewing for their test next week on Chapter 5. You can find the questions on page 324 in your textbook, and of course this is video number 2, so hopefully you've already watched video number 1 of this review material. In video number 1, we had only finished up to question 2a, and we were about to start question 2b, so let's do that together. It says 4 teachers and 5 students have volunteered to serve on the school's fundraising committee. The principal wishes to select the committee using a random draw, and he places each person's name on a slip of paper and draws 4 names. Now part B says what is the expected number of students? So to calculate expected number, well, we need a probability distribution. And to do a probability distribution, let's define our random variable x. Oops, ignore that. So we're going to let x be, well, if I want to calculate the expected number of students, then x should be the number of students. Okay, now again, ignore the weird penmanship. X is the number of students that are on the committee. So what are all the possible values of x? Well, is it possible to have no students on the committee and therefore have a committee of all teachers? Yes. I could have 1 student, 2 students, 3 students, all the way up to 4 students on the committee. So our job is to calculate the different probabilities for each of these 5 numbers of students. So these are x1, x2, x3, x4, x5, and this is capital X. Let x, meaning capital X, be the number of students. So how are we going to calculate each of these things? Well, first of all, I'm going to do it on a separate page so I have some more room, and we're going to use probability that we did earlier in the year, specifically from 4.7. So remember that when you have a committee, when you're choosing items or people for a committee, order is irrelevant. When you're selected for the committee, it doesn't matter if you were selected first, second, or third, and so on. So let's see. So again, I have 4 teachers, I have 5 students, and there's 9 people total on the committee. So what's the probability that x equals 0? In other words, the probability that I have 0 students. So if I want 0 students, I need to have 4 teachers and, of course, 0 students. And the sample space. Well, we saw the sample space in the first video. The sample space is that there are 9 people and I want 4 of them on my committee. So what do we do? So 4 choose 4 times 5 choose 0 is 1, and that's out of 126. And of course, let's turn this into a decimal approximation. 0.0079. So that's the probability in decimal form that there are no students on the committee. So I can go up here, and in my probability table, I can enter in 0.0079. And there's a decimal here. So now let's do the same thing, but now I'm going to do it for x equals 1. So now I want 1 student. So that means I need 3 teachers and 1 student. And again, 126, or 9 choose 4, is the sample space. So 4 choose 3 is 6. 6 times 5 is 30. So there are 30 ways of having 4 students and therefore 1 teacher on the committee. Oh, sorry. No, there isn't. Sorry. Math is good. 4 choose 3 is 4. I was jumping the gun a little bit. 4 choose 3 is 4. 4 times 5 is 20. So there are 20 ways of having 1 student on the committee, and as a decimal, the probability is 0.1587. So again, I'll go back and put 0.1587. So we'll do one more of these, and then I'll pause the video and kind of do the math without you. So now I'm going to put 2 students on the committee. So if there's 2 students, there must also be 2 teachers. And of course, 9 choose 4 is the sample space. So 4 choose 2 is 6, 5 choose 2 is 10, So that's 60 out of 126, which as a decimal is 0.4762. So again, I'm going to fill that in my probability distribution table, 4762, and then continue please finding the other missing values. I'm going to press pause in the video, but you won't notice it, so I'll see you in a split second. Here I am. And look, things are different. So I went through and I calculated the probability that there are 3 students and the calculator that there are 4 students, and I filled them into my table. And of course, I checked to make sure that I did my math right. And the way to do that, oh, don't sneeze on mic. The way that I did that is by adding these values together. And if they add to 1, then I'm much more likely to have done my math correctly. So here's the probability distribution table showing the probability for each of these numbers for x. And again, x is the number of students. And our goal was to find the expected number of students. So now what we have to do is multiply and add. Ugh. So I'm going to multiply this times this, and 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 then add all those values together, and that'll give me the expected number of students. So hold on, it's going to happen in an instant. Okay, so here's the math. So again, you're calculating them, you're multiplying each of x times p at x, adding all those products together, and in this case, I get expected value of 2.2224. Now, make sure it makes sense. Well, certainly, I needed to see a value between 0 and 5 because I can't have less than 0 students, and I can't have more than 5 students. Does it make sense that more than half of the committee is expected to be students? Yes, because there's more than half the people available are students. Not much more, but you'll notice my expected number is not much more. Now, please don't round this and tell me the answer is 2. Expected value is not an actual value that's ever going to happen. It's an average. So it doesn't mean I actually expect 2.22 students. That's impossible. It means that if we conducted this experiment of making a committee 1,000,000 times, then the average number of students on the committee would be 2.22. Okay? Excellent. So I hope that was helpful. Let's look at the next question I assigned. Oops, here it is, number 7. Find the probability that in 10 tosses of a fair coin, there will be exactly 5 heads, there will be exactly 8 heads, there will be exactly 2 heads, and there will be at least 2 heads. So tossing a coin is a binomial experiment, which is nice because we can use the binomial formula, well, the binomial experiment formula, which looks like this. The probability that x equals k is n choose k times p to the k times 1 minus p to the n minus k. Remember a couple things. First of all, you cannot use normal approximation for a question that asks you something exactly. And we couldn't use normal approximation no matter what, because if I toss a coin 10 times, the expected number of heads is 5. And you can only use normal approximation if the expected number is greater than 5. So don't even think about trying it in this question. So let's go ahead and do the math. So n equals 10 because I'm doing this experiment 10 times. The probability of success, I'm calling success heads, is 50%. And in this case, I want k to be 5. So A, the probability that x equals 5 is 10 choose 5 times 0.5 to the 5. So I want 5 heads. And therefore, I must also see 5 tails. So type that into your calculator. And I get 0.2461. And B, exactly 8 heads. So again, now k equals 8. So I want to see 8 heads and therefore 2 tails. So type that into your calculator. And I get 0.0439. Is that right? Yes. Okay, there will be exactly 2 heads. Now, logically, I know the answer is exactly the same as I got here. Because if I get 2 heads, I have to get 8 tails. So 2 heads is the same as 8 tails, and 8 tails would be exactly the same math. So it's this. Now, to show you the math, you would do 2 heads. So that's 10 choose 2, and then 0.5 to the 2, and 0.5 to the 8. And of course, we know that 0.5 to the 8, oops, typo, didn't happen. 0.5 to the 8 and 0.5 to the 2 is the same as 0.5 to the 2 and 0.5 to the 8. And based on the Pascal theorem symmetry, we know that 10 choose 8 is the same as 10 choose 2. So again, we know that this is the same as this. So D says, oh, that's annoying. Okay. So D says the probability that there will be at least 2 heads. Now, again, do not be tempted to use the binomial approximation. First of all, it's not possible because the expected number of successes is not greater than 5. Secondly, I never want you to use approximation in a question that says something like at least 2. Because the math to do at least 2 heads is really, there's only 2 steps, because the opposite of at least 2 is 0 or 1. So please don't use approximation in a question like that. So instead, we're going to do the opposite. Oops. So we're going to find the probability of 0 heads plus the probability, my computer's acting up, plus the probability of 1 head. And again, 0 plus 1 is the opposite of at least 2, because at least 2 is 2 plus 3 plus 4 plus 5, etc. So the probability of exactly 0. So I'm going to do 10 choose 0, and then 0.5 to the 0, and 0.5 to the 10, plus, now I want 1, so 10 choose 1, times 0.5 to the 1, and 0.5 to the 9. Okay, so calculating this out, what do we get? Okay, so for the probability of 0 heads, I get 0.00097666. For the probability of 1 head, I get 0.009766. So the probability of getting 0 heads, or 1 head, is just over 1%. And therefore, the probability of getting greater than or equal to 2 is 1 minus 0.01074, which is 0.8926. So, or 89.26%. So obviously I have to do something about what's going on with my pen, because it's something to do with the memory on my computer. And anyway, we're almost out of time for this video. So I'm going to stop here, and I will meet you in video number 3, hopefully with a working tablet. See you there.